sadece kontrol ettiğimiz bir şey olduğunu düşünüyorum. Yani accelerated charge particles, acceleration olduğunda şey oluyor.
Bak, radyasyonun tanımı o değil. Şimdi kitapta güzel bir örnek var. Çöp kamyonu örneğini veriyor. Mesela çöp kamyonundaki sinekleri düşün. Çöp kamyonu giderken sineklerin bir kısmı çöp kamyonuyla beraber gidecek. Bir kısmı da alıp başını çöp kamyonundan ayrılıp gidecekler. Şimdi bu ikisi, çöp kamyonuyla beraber gidenler bizim non-radiating field dediğimiz field var. Yükle beraber hareket ediyorlar. Sabit hızla giderse, bir yüklünün etrafında sabit hızla giden bir şey varsa ona şey demiyoruz, radiation demiyoruz. Ama bir kısmı da sonsuza kadar gidebiliyorlar. Artık yükten ayrılmışlar. Ona radiation diyoruz. Şimdi sonsuza kadar gitme kriteri ne demek? Şimdi sonsuza kadar gitme, sonuçta şunu düşünüyorsun. Sonsuzda bir küre alırsam diyorsun. O küreyi yeterince beklersem geçer mi? Bu elektromanyetik alana karşılık gelen enerji. Sonsuzdaki küreyi geçecek mi? Yeterince beklediğin takdirde. Şimdi bakıyorsun, bir küreyi geçen enerji dediğimiz şey Poynting vektörle orantılı. Poynting vektör sonsuzdaki bir kürenin üzerinden integrali sonlu olur mu, olmaz mı? Şimdi sorun şu, elektrik alan sıfıra gidiyor sonsuza giderken, manyetik alan sıfıra gidiyor. Poynting vektör dolayısıyla sıfıra gidecek. Ama yüzey de sonsuza gidiyor sonsuza giderken, sıfır çarpı sonsuz gibi bir belirsizlik var. Şimdi yüzey ama sonsuza gidiyor ama yarıçapının karesiyle orantılı olarak gidiyor. Şimdi yüzey yarıçapının karesiyle orantılı olarak sonsuza gidiyorsa benim sonlu bir enerji bulmam için Poynting vektörünün 1/r kare ile orantılı gitmesi lazım. Yani Poynting vektörü içerisinde 1/r kare ile giden bir kısım var mı yok mu? Şimdi Poynting vektörü dediğin elektrik alan çarpı manyetik alan. Boşlukta elektrik alanla manyetik alan zaten birbiriyle ilişkili. Dolayısıyla elektrik alan ve manyetik alan aşağı yukarı benzer davranıyorlar çok uzak mesafelerde. İkisi de 1/r gibi davranması lazım ki, ya da ikisi de sabit olabilir. İkisi de ya 1/r gibi davranacak, localized bir source'tan çıkıyorsa. O zaman 1/r karelik bir pointing vektörüm var, sıfıra giden. Onu bir yüzey üzerinden, r kare ile yüzey alanı artan bir yüzey üzerinden integralini alırsam sıfıra gider. Sabit bir şey çıkar. Oradan da diyorum ki eğer elektrik alanda 1/r şeklinde giden bir kısım varsa o kısım benim radiation field'ımdır. Tabii şu da var. Mesela ilk başta hatırlarsanız elektromanyetik dalga plane wave'lerden bahsettik. Şimdi plane wave'lerden bahsederken plane wave'ler yayılmayan dalgalar. Şöyle gidiyor. O zaman sonsuzdaki bir küreyi düşünsem bile sonsuzdaki bir küreden sadece belli bir alanından geçecek. O alanda sabit. O zaman ya sabit bir alan kürenin bütün yüzeyine yayılmıyorsa o zaman sabit kalmasını bekliyorum. Elektromanyetik dalgamın. İşte o plane wave'ler. Kürenin bütün yüzeyine bir şekilde yayılıyorsa o zaman enerji bir defa 1/r kare ile yayılsın ki r kare alanıyla çarptığım zaman sonlu bir enerji bulayım küreden dışarı geçen. O yüzden diyorum ki 1/r ile gidiyor bu tangential elektrik alan. Sonuçta toplam elektrik alan ne var? Radyal komponenti var. Bir de tangential komponenti var. İkisinin toplamı. Uygun birim vektörlerle çarpılmış halinin toplamı. Radyal komponent 1/r kare. O bir katkı vermez enerjime. Sonsuzdaki kürede geçen enerjiye bir katkı vermeyecek 1/r kare olduğu için. Bu verecek. O yüzden diyorum ki bu benim radiation komponentim. Sonuçta elektromanyetik alan dediğim şey ikisinin toplamı. Ama bir komponent radiation'a karşılık gelecek, öbür komponent radiation'a karşılık gelmeyecek. Diğer komponent benim yükümün etrafında lokalize bir enerji yoğunluğu oluşturacak. Yükümden pek fazla uzaklaşamayan, yüküm nereye giderse o da oraya gidecek. Bu komponent ise sonsuza kadar gidebilecek.
Bu PW'da özel dediğimiz bir şey yok değil mi hocam?
Yok yok. Yani sonuçta asıl ifademiz bu. Şu. İvmelenen bir yük olduğu sürece senin radiation field'ın olacak. Yani bir sistem bir radiation yaratıyorsa mutlaka ivmelenen bir kısmı olmak zorunda. Theta sıfıra gidiyor. Şekil bu.
Şunlar şu tarafta da olmaz, şu tarafta da olmaz.
Aynen öyle.
Şöyle balon gibi hani maymun.
Şu tarafta bu yönde, bu tarafta bu yönde. Yani radiation'ın tanımı ne diye sorarsan, yok ivmelenen charge'ların yarattığı elektrik alan vesaire vesaire değil. Radiation'ın tanımı sonsuzdaki bir küreye geçebilecek olan elektromanyetik enerjidir. Onu kimler yaratabilir? İvmelenen yükler yaratabilir. Okay, any other questions about this one or anything else you want me to review? You were asking about the potentials. No? Okay. And if you don't ask anything, there is another derivation which we skipped because it was kind of a technical derivation, but we didn't really derive the retarded potentials. I just wrote it down and show that it does satisfy our equations. But we can also derive it. I mean, as I said, it's a technical mathematical derivation, but I think it's a nice application of what you had learned in 209 and 210, in the sense that we will be talking about Green's functions, we will be using complex integrations, etc. If you are interested. You see, what we are interested in solving is this equation, 1 over c squared del squared by del t squared minus the Laplacian of phi. This should be equal to, if this is the scalar potential, the equation was rho over epsilon 0. So this is what we want to solve. And this phi depends on r and t. So rather than solving this equation for an arbitrary rho, what we can do is first look for the corresponding Green's function. Let's look for the solution of this equation.
Green's function.
Did you study Green's function? No?
Special function.
So you never saw this equation? Okay. Then we are not driving it. I can give you some reference if you are interested in. Okay, so what are you interested in? What should we do in the remaining of the semester? Well, not much left. We have 1 hour today, Friday no lectures. Monday we can have some lecture. Next Friday, the last day, we won't have any lecture.
Hocam şimdi biz 2 dönem boyunca bir sürü şey öğrendik ya. Bunların hepsi kuantum mekaniğinde falan da kullanılıyor mu? Her yerde geçerli mi öğrendiğimiz şey?
Well, you see, what did we learn? What did you learn?
Elektrostatik, manyetostatik. Ondan sonra elektrodinamik.
You see, okay, in electrostatics, what did you learn? You mainly, the main thing you learned was how to solve this equation. Correspond to a given boundary conditions. That is what you had learned. Well, in that case, we called rho to be the charge density, phi to be the scalar potential, etc. But the thing that you will be using all the time is how to solve this equation. Well, what is Schrödinger's equation in quantum mechanics? Well, it's the same Laplacian. Sometimes you have some position-dependent functions added to the Laplacian, sometimes not for the free particle. But mainly in quantum mechanics, you always use the Laplacian. So does this tell you that, okay, whatever you learn over here, will you be using in quantum mechanics or not? But we have studied the Poisson's equation and Laplace's equation, which is quite common. We just applied it to problems in electromagnetism, which will be also valid in quantum mechanics. Then we had seen that we can talk about the scalar potential, the vector potential, how the charges move in a given electric and magnetic field. Well, the corresponding Schrödinger equation is this one. So this is how a particle in an electromagnetic, this is the Schrödinger equation for a particle in an electromagnetic field. So you will be using the concept of the vector potential, the scalar potential, etc. Well, there's still the problem of gauge invariance. You see, I can change A to A prime, which is A plus the gradient of lambda, and phi to phi prime, which is phi minus del lambda over del t. I can always make this change of variables, but then phi prime and A prime, they are different than A and phi, so the solution will be different. Well, then this phi prime, psi prime, just becomes psi e to the power q over I, q over c, a, lambda, times psi. Q over c h bar. Let me add h bar also. Yes. Well, let's say, I mean, if you want, we can continue discussing quantum physics, quantum mechanics, etc. But for the time being, let's restrict ourselves to relation of electromagnetism with quantum physics. You see, one thing that I think you are missing kind of in all your courses is, okay, on one hand, we are studying electromagnetic phenomena, like the radiation, when you do quantum physics, you will look at how the light comes out from the atom, how the atom emits light. There will be some similarities, etc. But here, okay, on one hand, we are looking at, given a charge distribution, what is the potential, etc. But that's probably the part that most of you will use the least. Most of the time, what you will be used is the techniques that we have used in this course to study electromagnetic phenomena. Those are the things that you will use everywhere. Laplace equation. If you add some constant to it, to the Laplace, it just becomes the Helmholtz equation, etc. But in one form or in another form, whatever you study, it will always contain some Laplacian somewhere. Well, Laplacian is nothing but the second derivative generalized to 3 dimensions. The second derivatives, we always have second derivatives everywhere popping up. So that is what you will use everywhere. Is that using what you learned in this course in some other place or not? I would say yes. This is probably the first course in which you are studying the Laplacian in such a detail. Or if I go back to your questions about radiation, what is radiation? It is the electromagnetic field emitted by an accelerated charge. It is the electromagnetic field in such and such a system. No, that's not how we define radiation. The radiation is the energy that can escape to infinity. If there's an accelerated charge, you look at the energy. If it can escape to infinity, then you have radiation. If you have some other system, you look at the energy. If it can escape to infinity, then you have radiation. The same thing holds here. There is a Laplace equation, which you will see in many places, many places. And the way we solve here is more or less basically exactly the same as in every other place. When you look at quantum mechanics, when you look at statistical physics, when you look at I don't know what, you will be dealing with using exactly the same methods. You can look at the diffusion process. For example, what happens when you put some ink drop in water, how does it spread out? That contains Laplace equation.
Next question. If the radiation energy escapes to infinity, so we should have a lot of radioactive energies around us.
Lots and lots of them. From all over the universe, there is radiation. So what do you mean by harmful?
I mean, it makes cancer and stuff.
How does it make cancer?
As I remember, in cells there are some factors that control the division of cells.
Okay.
And that's radioactive wave or energy. And destroys that.
How does it destroy it? You see, did I destroy you?
No.
I hit you, no?
Yes.
But not strong enough.
So they are not strong.
No, most of them are not. I mean, you have to have electromagnetic waves that carry a large amount of energy. They should be at very high frequencies. In that case, they will have the photons, the corresponding photons will have a very high energy, and that energy can break the bonds, so change your cellular structure. And some of them might cause cancer. But most of this projector, the light from the projector is a radiation. It can go up to infinity, but it won't cause me the cancer. Or the light reflecting from you, it won't cause cancer. Or the light that you emit, you're emitting light because you have a finite temperature. That doesn't cause cancer. But they are all radiation. You are radiating. You are not radioactive. That is usually used in a different context.
So, for example, we put a lamp in a focal center of a lens, for example, its light goes to infinity. So, is it radiation again?
That is radiation. I mean, even if you don't do it, it is still radiation. Just pick up a light. Well, you say that, well, it doesn't go to infinity. Well, it does. Because the intensity of that light decreases as 1 over r squared. So if you just look at it from a very far away point, its intensity is so small that you cannot see it with your eyes. But if you could measure its intensity at every point, multiply it with this sphere with radius r, you would get a finite value, which is independent of the size of the sphere. That is radiation.
Bir tane foton olmasın diye yetiyor.
Yeah. The only criteria for radiation is that there should be some energy which is able to go up to infinity. That is the only definition we have. There is, of course, ionizing radiation, which can break the bonds, which can ionize atoms, molecules. That is what is considered to cause cancer. But not all radiation is ionizing.
Hocam, radyoaktif dikeydeki radiation nasıl oluşuyor? Orada bir acceleration yok.
So what do you mean by radioactive decay?
İşte uranın yarılanması mesela.
Okay, so what does the uranium do when it decays?
Its mass turns to the
No, I mean, what happens to the uranium nucleus?
İkiye mi ayrılıyor, küçülüyor?
It splits into two. Let's say you have one nucleus. It splits into two. So let's say, just for sketching purposes, it splits like this. On one side you have this half. On the other side you have this half. So do the remaining nuclei keep that shape? Stay in that shape? No. What do? Become spheres, more or less. Well, there you have the acceleration of charges. Now, this is, of course, the semi-classical description, let's say. In that, at that scale within these processes, you have to take into account the quantum mechanical effects. But the basic idea is still there's a rearrangement of charges, which is just another way of saying that there are accelerated charges there. They will emit radiation.
O zaman buna göre bu iki tane proton çarpıştığında açığa çıkan parçacıklar da...
Sure.
Peki gerçekten biz gözlemliyor muyuz öyle bir şey?
Well, let's see. If I'm not wrong with the numbers in LHC, these CMS and Atlas accelerators, the amount of radiation they are subject to in a year is equal to, I think, 3 atomic bombs.
Biz şimdiye kadar hep kritik olarak bunu düşündük değil mi? Biz şimdiye kadar hep elektronu klasik parçacık
Sure.
gibi düşündük. Kuantum olarak düşünürsek hani bir diskret enerji var. Yani direkt ivmelenip gidemeyecek. Arada bulamayacağı pozisyonlar olacak. O zaman bunun yansımasını görmüşler mi?
Well, let's see. You have already studied the atomic spectra, right? To some extent. You know that there is a discrete energy levels, and in these discrete energy levels, when you have a transition, there is an electromagnetic radiation. So there is this level, let's say, there is this other level M. And when the atom from the nth level, the electron decays into the mth level, it emits a radiation with a frequency, let's say omega n m. This is equal to En minus Em over h bar. Now, of course, the question is, how do we describe this time-dependent process? Well, that is kind of a technically complicated problem, but let's see. Within this interval, as the atom is making a transition from the nth state to the mth state, it will be in this state. The wave function will be A at t equal to, at some t equal to 0, psi n of r plus b times psi m of r. This will be the wave function while it's making this transition. Or if you write the time dependence, a times e to the power minus I over h bar, En psi n of r plus b times e to the power minus e over h bar, Em of t psi m of r. Now, the radiation is due to the acceleration. Acceleration is nothing but the second derivative of the position. So let's look at what is the average position of this particle as a function of time. Let's see if the second derivative, what will be the average position? How will it behave? Well, there will be a component a squared, the average in the nth state. There will be a component b squared, which is the average times the average in the mth state. But there will be also the mixed terms. And those mixed terms will have this form. Twice the real part, let's say R and M. I will define what that is in a moment. A star B, e to the power I over h bar, En minus Em of t. A squared Rn plus b squared Rm plus twice the real part of a star b. Let me write it in this form, R and M e to the power I omega t, where this R and M is just psi n star R psi m. This is the average of R. What is this motion? Oscillation with frequency given by omega mn. So basically the particle is oscillating, its position is oscillating with a frequency of the emitted radiation. If you look at R double dot, well, the first terms there, these are independent of time. I only have that one. Minus omega mn squared R. No, not R. Times twice real part of a star b, R and m e to the power I. It's accelerating with an acceleration determined by the frequency of the emitted photon. So in this sense, there is no discrete transition. In between, the average position is oscillating. You see, when you say about the discrete energy levels are discrete, not the position. The electron can still be everywhere. You can find the electron everywhere. There is no restriction on the position of the electron. The only restriction is on the possible energies of the electron. Well, the problem is these two states that I wrote over here, these are not in position space. So there's no point in talking about an electron at this point. There's no position here. It's just a schematic view of the possible energy values of the electron. If this is the atom, the electron can be here, here, there, wherever you want. But even if you find the electron over here, its energy will be En or even En, whatever its state is. But of course, the problem is, since the Hamiltonian and the position do not commute, when you measure the position, you cannot talk about its energy anymore. When you measure the energy, its position can be anywhere. When you measure the position, its energy can be anything. So what's your lucky number? 10. Okay, the problems start at 22, so 32. Other questions? So this is the question. In my book, it is 32. A charged particle traveling, blah, blah, blah. So we have this x-axis. There is a particle coming from -infinity, and there is a potential energy barrier. So between x is equal to, let's say this is the u-axis, this is x is equal to 0, this is x is equal to L. So the potential is u0 here. This is u0. This says that even if the initial kinetic energy is less than u0, the particle can pass through because of the radiation reaction. So you see, the problem is if there is an acceleration, if the charge is accelerating, due to this acceleration, there is the radiation emitted, and due to this radiation emitted, there will be a force acting on my particle. So that's what we call the radiation back reaction. And the acceleration of the particle is given by the potential, basically. So if you write the equation, mass times A is equal to mass times tau dot A dot. Well, this is our radiation back reaction. Tau is the time scale plus the force. This is m tau A dot plus u0 minus Dirac delta of x plus Dirac delta of x minus L. This is the equation we need to solve. Well, rather than studying this problem, let's look at, I mean, we had seen that there was some kind, this radiation back reaction is kind of problematic. So it accelerates on its own. The particle can accelerate on its own. It can accelerate exponentially if there are no external forces. But then there was this kind of loophole. If there are no external forces, it will stay. Its initial acceleration will be 0, and its acceleration will always stay 0 due to the initial condition. But this doesn't really save us. Let's say we have a general time-dependent force. Nope, sorry. Let me first look at this one, this problem. How can we solve this problem? Well, you see, in this problem, force depends on x. So this won't be the general solution of that one, but we can deal with that force later on. Let's start with this one. How can we solve this differential equation? Let me write it in a slightly different form. Tau, or let me even cancel that. Tau A dot minus A over tau plus F over m, this is equal to 0. This is equal to minus F over m. How do we solve such a differential equation? Tau is just some constant. M tau, yeah, yes. Some constant. Now forget about the homogeneous part. Let's look at the inhomogeneous one. Yes, the simplest thing will be an integrating factor. So the idea is, let's see, if you have f times g, this is f dot times g plus g dot times f. So just convert this into this form where, for example, I can take g to be a. I should multiply this, the left-hand side, by some f. I don't know what yet. But I should multiply it by some f so that the left-hand side I can write as a total time derivative, a single one. So I can integrate both sides with respect to time to obtain this product, and that would allow me to determine what A is. Now, in this case, the integration factor will be just simply e to the power minus t over tau. Well, how did I guess that? You see, if I multiply the left-hand side by f, here I have the fa dot, just like this one, fa dot, but here I have minus f over tau instead of f dot. So f dot should be minus f over tau, and that is possible with this factor. Now, the left-hand side is nothing but the total time derivative of e to the power minus t over tau times a. And that tells me that e to the power minus t over tau times a is nothing but minus f of t prime over m tau e to the power minus t prime over tau, let's see, from t0 up to some t. Or a is equal to minus from some t0 up to final time t, f of t prime divided by m of tau e to the power minus or plus t minus t prime over tau. Well, this is kind of problematic because you see the acceleration at the time t depends on the forces at every time between some t0 and t. It doesn't depend only on the force at t. So this is not something we would expect. You see, Newton's second law just tells me that acceleration should be the force acting on my object at this time divided by the mass. So this just doesn't hold here. So that is actually one of the other problems for this radiation back reaction. Now let's go back to our initial problem. How do we solve this equation? Well, you see, whenever you have Dirac deltas, they are kind of problematic functions. You would rather avoid them as long as possible. Well, I can avoid them if I consider this equation for x less than 0. Or x is between 0 and L, or x is larger than L. So I have my particle. I can determine its acceleration, let's say, until it reaches my potential barrier. Then I have to do something else. After it passes, if it can, the x equal to 0 region, until it reaches the x is equal to L point. And I still need to consider what happens over there. And if it manages to pass that point, then I can see what happens after x is equal larger than L. So in all these three regions, my equation is this one. Ma is equal to m tau a dot. I can cancel the m's. This tells me that a dot is just a over tau, or a of t is some constant times e to the power t over tau. This is my acceleration as a function of time.
Potential neden sıfırlık?
Well, you see, I'm not taking the potential to be 0. I'm taking the force to be 0. The force only appears at x is equal to 0 and x is equal to L. There is no force anywhere else.
Peki bu region içinde?
It is still 0. You see, the force is the gradient of the potential, the derivative of the potential. Between x is equal to 0 and x is equal to L, the potential is constant, so there is no force. It's a constant potential.
In A of t, do we need dt after the integral?
Sure. dt prime.
O zaman force sadece sıfırla L'de mi bir anda etkili?
Yes. There's an infinite, I mean, that is the potential barrier. There's an infinite force when x is equal to 0 and when x is equal to L.
Ama potential.
So, you see, force is not potential. Force is the derivative of the potential. The force can be very small, but if its derivative can still be huge. You see, you can have such a potential. Its derivatives are huge, the slopes are huge, but the potential is very small. There's no problem with that. Show that because of the radiation reaction, it is possible for the particle to tunnel through the barrier. You see, in quantum physics, what you see in quantum physics is that if you send a particle, whether charged or neutral, it doesn't really matter. If its energy is less than the height of the potential barrier, classically it cannot go through. But quantum mechanically, the wave function doesn't just go to 0 because of this finite height. The probability of finding the particle on the other region turns out to be finite. So we say that quantum mechanically, the particle, although cannot pass to the other side, it can still go through. So we don't really know how does it really happen. I mean, we just find it weird. We just say, okay, it's a weird quantum phenomena, but do we have a deeper understanding? Is there a deeper reason how it just goes through? How can we describe it? So maybe this is the answer.
Hala öyle bir şey yok mu? Cevap veremiyor.
We know it happens. I mean, all your electronic devices are basically work because of this tunneling phenomena.
Ama nedenini alamıyoruz.
Well, I mean, the only answer we have for the time being is quantum mechanical phenomenon.
Cevap değil ki.
Well, you see, F equal to ma, is that an answer? Now, I mean, whenever you do physics, you start from some point. In classical physics, F is equal to m times a is your starting point. Your zero approximation, 0 point. You start your derivations using Newton's three laws, including F equal to ma. In quantum physics, there's no derivation of F is equal to ma in Newton's mechanics. In quantum physics, we start from, if you like, the Schrödinger equation. And then we just discuss what the Schrödinger equation predicts. Tunneling is one of those predictions. And we observe it in nature. There is no derivation of the Schrödinger equation, or there is no derivation of the tunneling phenomenon. So we would rather like to have an explanation why even quantum mechanics exists. So this is my acceleration. What is my velocity as a function of time? If that is acceleration, it's the integrate. It's just c times tau e to power t over tau plus d. What is the position as a function of time? Integrate once more. It's, okay, c times tau squared e to power t over tau plus d times t plus e. This is x of t as a function of time. Okay, so let's start with, let's say that at t is equal to t0, x of t equal to 0, let's say it's at 0. It reaches the barrier at t equal to 0. So for t less than 0, my solution is, let's say c0, tau squared e to power t over tau plus d0 t plus e0. So x of t equal to 0 is c0 tau squared plus e0. This should be equal to 0, which tells me that E0 is equal to minus C0 tau squared. So x, let me put x0 at t. This is equal to C0 tau squared e to power t over tau minus 1 plus d0 of t. This is my solution for t less than 0. My solution for t larger than 0, let's say x1. Okay, so let me just say x at t1 is L. Okay, my particle is coming. It hits at t equal to 0, it hits the x is equal to 0. So if it is moving, it will hit at t equal to t1, it will hit the x is equal to L region. And that is my t1. For t between 0 and t1, my solution would be, let's say x1 of t will be c1 tau squared e to power t over tau minus 1 plus d1 of t. I again impose the condition that at t is equal to 0, this solution should still be 0 at t equal to 0. But of course, the C1 and D1, they can take different values. And then for t larger than t1, my solution, let's say, is x2 of t. And that is equal to, let's say, C2 of tau squared e to the power t over tau plus d2 of t plus E2. I have one more condition, x1 of t1 should be equal to x2 of t2. T1, sorry. Yes, these are both equal to L. Well, it's a continuous function. The position changes continuously. You see, the velocity need not change continuously because the acceleration can be infinite. There are regions at which the acceleration... Well, you see, let's see. Now, okay, we can continue maybe on Monday. This is what I will do. We have these many constants. I don't know what C0 is, D0 is, C1 is, D1 is, C2, D2, E2. I don't know what they are. So I have to impose some conditions which will allow me to determine those coefficients. One thing I have to do is I have to determine some matching conditions at t is equal to 0 and t is equal to t1. Now let's look at this one. Let's go back to our equation. This was our equation. Now let me integrate both sides from x is equal to 0 minus to x is equal to 0 plus. Now, of course, the first question, is the acceleration finite or not? Well, you see, I will assume the acceleration is finite but not necessarily continuous. If the acceleration is finite, you see, this is finite, this is a finite number. I'm integrating over an interval that has 0 length. So the integral of m times a from 0 minus to 0 plus over x is 0. 0 is equal to m times tau, integral of dx from 0 minus to 0 plus let's say dA by dx times dx by d tau, dt. This is dA by dt. Plus or minus u0. This is the integral of this term. The integral of this one is minus u0. The integral of Dirac delta is over this interval is just 1. So this tells me that okay, so this is one condition I have, mt from 0 minus to 0 plus of dx a dot, let me just leave it in this form, is equal to u0. Or well, this will basically relate my acceleration on the left of x to the acceleration on the right of x. So this will give me a relation between E1, C1, D1 and C0, T0. Well, maybe we should multiply this some other quantities so that we can integrate it over. Okay, I can say that let's just integrate over dx over v. This will cancel this one, so I will end up having a at x equals 0 plus minus a at x is equal to 0 minus will be that number over there. Of course, x is equal to 0 plus, I can just say t is equal to 0 plus. Instead of x is equal to 0 minus, I can just say t is equal to 0 minus. Well, this tells me that the acceleration is not continuous. You see, the acceleration between, the difference in the acceleration between t is equal to 0 plus and t is equal to 0 minus is a finite number. So it's definitely not continuous. But it's finite. That's one thing I assume, the acceleration is finite. Well, I need to repeat this thing for the x is equal to L. And in that case also I will get the acceleration of the particle when it is at the position x is equal to L plus minus the acceleration of the particle when it is at the point L minus. This will be equal to u0 minus u0 divided by m tau v when x is equal to L. This is another condition. Well, the other conditions I have is V0 at t is equal to 0 should be equal to V1 at t is equal to 0. And V1 at t is equal to T1 should be equal to V2 at t is equal to T1, basically because acceleration is finite. The velocity, the speed of the object cannot change instantaneously. It should change continuously because acceleration is finite. So I have two conditions here, two additional conditions here. I have four additional conditions. How many unknowns I have? 1, 2, 3, 4, 5, 6, 7 conditions I have. The additional conditions I need is the initial conditions, which I didn't specify. Well, we need to leave. Anyway, we can continue on Monday if you show up.